Hello, dynamic students. Here's an example. This is from chapter 15, section 15.5 from our textbook, which is Beer, Johnston, and Cornwell. It's the 10th edition. So here's an extra example problem to try to help solve the homework. All right, so we have these two collars, collar B and collar A, and they're constrained to move on these bars. And there's a link between them. That's bar AB. So collar B moves downward and to the left. So let's see, make sure I have the pen turned on here. Yep, pen turned on. Nice red color. So it's moving down and to the left. So in that direction, and at a constant velocity of 1.6 meters per second. At that instant, shown when theta, which is right here, equals 40 degrees. Determine the angular velocity of the rod AB and the velocity of the collar A. Well, I made this in SolidWorks right here so that we could see this is the actual angle going on here. So this is the actual 40 degrees, and here's some dimensions so that you can see what's going on. And I even made a little animation here so you could see as this thing is moving. So the top one's moving down and to the left, but the other is moving downwards. Now, one aspect of this is what we're going to look for back here is we're going to try to find the angular velocity. That's the angular velocity of this bar. So this bar is rotating. So as I hit this animation, I want you to try to imagine it's translating, but it's also rotating. So look at the bar and let's say look at its angle. Look at the angular position of it, and you can see that the angle of the bar is changing as it's moving. Therefore, it's rotating. Okay, so this is the game that we're playing. Is we're going to go ahead and let's see, I'll actually use a little ruler right here so I could make a straight edge on my touch screen, and I'll set this up. And I recommend doing something along these lines when you're doing a problem, is to make a very accurate drawing. It will really help, especially when there's angles involved. So our technique is to use 3 diagrams to draw the bar 3 times. And what we do is we set up, okay, I accidentally touched it, so the touch screen is working. All right, so what we do is we set up our positions here, and this is one of the reasons why we're going to make an accurate drawing, is we're going to try to make sure that we get the angle of the velocities correct, right, compared to the angle of our piece. Now, I'm getting these weird stray marks right here, so you'll have to excuse me. I've been trying to figure out on my new Surface Book with these stray marks. Now, we already had the animation where we showed the direction, so we kind of know the direction based on the animation, but let's pretend we don't know, okay? So instead of drawing this, I'm going to draw a dotted line. That means my velocity at point A is constrained right there. So my velocity at point A is unknown. So my velocity at B is known, and by the way, we also know this angle right here. So we have to be a little bit careful with this. I'll draw it up here. We could say that this is a triangle right here of 60, so that's 90, so this has to be 30 degrees. So that's an important step right there. We make sure that that's 30 degrees right there. We also know that this is 40 degrees right in here, as the problem says. What I'm going to do now is on this second diagram, let me write out our fundamental equation. Is the velocity of A is equal to the velocity of B plus, that should be A, plus, oh, come on, stop that, velocity of A with respect to B. Okay, so this for us, that's the translation term, and this is going to be the rotation term. These are vectors, diagrams. So our procedure is to, at point A, that's going to be the point that we reference. It's going to be our reference point right here, point A. We're going to use what we know, and we'll make it a translation at A. Okay, so we have the velocity of B right here is also going to be the velocity right here, the velocity of B. Okay, so that's going to be the translation that we make of this. And I'll save that verse for a second. Come back up here. Being a touch screen at the same time, that's the problem here. Now, we used B as the reference here as a second part, so we're going to go ahead and treat it as if it's pinned and fixed at that location and that it's going to rotate. Now, we have to pretend that we don't know the motion of it, because in many problems it's not going to be easy to detect what the motion of the piece is. So I go ahead and I assume that it's going to be a positive counterclockwise rotation. So this is going to be the omega AB for this. And that's going to cause a velocity perpendicular right here. And once again, I'm getting a little angry at this thing. Okay, come back up to here. The velocity A with respect to B right here. So this is the velocity of A with respect to B. My diagrams are starting to bleed over into my equation there. All right, so I'm going to go ahead and assume that this A is positive. Okay, so that's when we have velocity of A that I'm initially going to choose. I'm going to somewhere over to the side make sure that I establish what my positive directions are going to be. So I draw my little coordinate axes. All right, so here is the method that we're going to use right here. Let me start with another pen here. I'll go green, Christmassy looking. We're going to go in the X direction. Okay, we're start out in the X direction, and we're only going to focus on point A, and that's what our equation is doing. It's focusing on A, and it's saying, okay, the velocity at A is going to be equal to the velocity of B. That's going to be the translation, so it's going to translate. By the way, that's supposed to be an angle right there. So this is also 30 degrees, even though it doesn't look like it in the diagram. So it's going to be in the X direction. We'll just proceed for the thing. So in the X direction, A is going to be 0. There's no velocity X direction because it's constrained. And then it's going to be equal to the velocity in the B direction, but positive is to the right. So this is, we know it's going to the left. So it's going to be negative VB times the cosine of 30 degrees. There's my stray marks are going up again. Now we come over to this, and now we only want the X component of VA with respect to B. We need to make sure we be very careful with our angles right here. We want to know what this angle is. Going through here, come on. All right, we know that this angle right here is going to be 40 degrees. So what I do is I look at that and I take a look at this right here, and I know that that has to move 40 degrees that way. So this has to move 40 degrees. So I know that that's 40 degrees. That's just my way. There's many other geometry ways of establishing that, but that's my method. And okay, so the X component of the velocity A with respect to B is to the right. So that's going to make it positive, and I'll just keep these as symbols. That's velocity of A with respect to B, that's the magnitude of it, times the cosine of 40 degrees, right? But we can replace this right here. Let's move it to another color. Let's go blue. We know the velocity of A with respect to B is going to be equal to omega AB R, and if we could call R in this case, we could call R what did I call it? A with respect to B, okay, right? Because this is B right here, and this is A, so this distance is RA with respect to B. That's just going with our nomenclature. So we can replace that with omega AB RA with respect to B. So I'll rewrite the thing out because I'm taking plenty of space here. I know my velocity B with respect to A is going to be 1.6. So it's negative 1.6 times the cosine of 30 degrees plus my omega AB times my RA with respect to B, which is going to be 0.5 meters. All right, I'll change it into meters right away. And 9 times the cosine of 40 degrees. And now I'm able to solve for my omega AB, which I find to be positive, a positive value. So I know that I chose the correct direction here. That's the one thing that I left out. Like all the other directions I knew, that one I assumed was going to be in the counterclockwise direction. And I get that to be 3.618 radians per second. And this is going to be the answer here, but for a complete answer, we need to make sure that we include the direction. Okay, now that's the first part. I'm going to go ahead and erase this so I can use this same diagram, because on mine, I would be doing that. On the paper, I'd have enough room. I'm not exactly happy with that little quirks of the Surface Book so far. I'm going to give Microsoft a pointed letter. Okay, take purple for a little variety. Now I'm going to go in the Y direction. And in the Y direction, I assumed that VA was positive, so I'll just say VA. Now, I kind of know it's going to be in the negative direction, but let's go ahead and assume it's positive and pretend we don't know. Now VB is definitely in its Y component is definitely in the Y direction. So that's going to be negative according to our sign convention. So that goes negative VB but times the sine of 30 degrees. And then also now we know, let's say we can we know that the Y component of the VA with respect to B is also negative. So I'll just go ahead and write that, even though I could start skipping steps here. I won't do it. 40 degrees, and of course, silly little thing, little quirk right there. Okay, so we have that set up, but we know that we can replace this right here. So we say VA is equal to, come on, negative 1.6 sine of 30 degrees minus omega AB, but we know what omega is already. We had that as 3.618 and times R, which is 0.5 meters, times the sine of 40 degrees. We find that VA is equal to negative 1.963, and this is meters per second because we kept everything in meters. So it's negative, so we guessed wrong. That's the implication of the negative, because we guessed in the positive direction. I always by default pick the positive direction. So we say that VA is equal to 1.96. And when we have 1 as the first significant figure, we can go for 3 sig figs. When 1 is the first digit, I should say, we could go 4 sig figs. I know that made a whole lot of sense. And we could say that in the downward direction. Of course, once again, we never want to put a negative with an arrow, because that's the double negative, right? It kind of reverses the sign of the arrow that you write. But this is the complete answer. So that's the procedure we want you to follow. It's pretty laid out there, because when problems get more complicated, you're going to have to keep track of everything. So there are many problems you can use intuition and get the answer really quick. But we want you to start being a little bit more disciplined in the way that you lay the thing out. One of the most important aspects is making this diagram. This diagram is going to be necessary, and when we get to the acceleration parts, when we start to try to find the accelerations due to the motion, we're really going to need these diagrams. So hopefully this helps with this homework, and that you start to pick up on how to approach these problems.